Yes, hi. Today I would like to discuss about how to approach integration problems, which means what integration technique you will choose at each step of finding a process. Because let's say if you are looking to find an integral of some function, definite or indefinite, you might have to use more than one integration technique. But just on this video I would like to concentrate on what to do in each step of the way in finding the final integral. So, let's start. The first one, it's of course, you start from the easiest, which is when you have to apply directly a rule of integration, like the integral of x to the n dx is equal with x to the n plus 1 over n plus 1. The integral of e to the x is e to the x, etc. So all these functions that we already know the integrals. So now the second step, if it's not one of those, the second easiest step, it will be substitution. So now, when do we use, when it's, we have a clear signal that we have to use substitution. Let me tell you, what happens when you have to find an integral of a function, let's say f of x dx, and you use substitution. What you do is you substitute part of the f of x equal with, let's say, some other variable u. So let's say a part of this, which can be, let's say, the g of x. So we substitute u equal with g of x, and then what do? We take the derivative of this u with respect to x, and let's say this is equal with g prime x. So now, if you solve for this dx here, you will have that dx is equal with du over g prime x. Now, how this has to do with when you have to choose to integrate by substitution. You see, if, let's go back to this here. So, and let's substitute the dx from here. So what we will have, of course, some new function f of u, and then you will have, instead of dx, you will have du over g prime of x. So if on this function here you have exactly this here somewhere, so this cancels, and that means that you can proceed and find the integral by substitution. So what's my point? My point is that whenever you have the derivative of what you substitute equal with u is on the numerator, is part of the product in the numerator of the initial function, then for sure you have to use integration by substitution, because again, when you do all the necessary steps, this here will cancel with this here, and then you can find the integral. So, I can do here, and actually to be more precise, this here, whatever you have here, can be any linear multiple of this, because, if it's just a linear multiple, the main thing is to cancel whatever has the x. Now the linear multiple just comes outside of the integral, so it doesn't affect the integral that you have to find. Let me do let's say, a very simple example. Let's say you have to find the integral of 2x times the x squared plus 1 dx. So, I mean, here, if you see, you can go and substitute whatever u equal with x squared plus 1. Of course, from here you have that du over dx is equal with 2x. And now that means that the dx is equal with du over 2x. So and now if you go back to the integral that you have to calculate, what you have 2x. Now instead of all these you put u, so you have the square root of u, and instead of dx you put du over 2x. So this cancels with this. Now you just have to find the integral of the square root of u with respect to u, so that's u in the 1/2 du, and this here it's the integral of this is u to the 1/2 plus 1, so u to the 3/2 over 3/2 plus c. And of course the integral of this is I mean, because we have to find the integral with respect to the initial variable, which in this case is x. So the integral of this is u, where we said u is equal with x squared plus 1, so that should be x squared plus 1 in the 3/2, so that means that it should be square root, and it should be to the 3rd power, and of course over 3/2, so that means if you do this composite fraction symbol, so that should be 2/3 plus c. So and that's the integral of this function here. So I mean that's to show you when you have to use the substitution technique in order to find the integral. So again, whenever in your initial function you have the derivative of what you substitute equal with u, so then immediately it's integration by substitution. Okay, and just to make clear again what do I mean? I mean, from the example we substitute u equal with x squared plus 1, so you see that this here, which is the derivative of what we substitute, it's already here. So immediately, because if you then go and you substitute back the dx, this cancels with this, and then you just have the integral of u with respect to u, of some function of u with respect to u, which of course you can, it's very easy to find it. So, and of course when we say substitution, we mean of course, I mean there are of course some easy substitutions, and of course there are some more difficult problems that they can be solved by substitution, like trigonometric integrals, trigonometric substitutions, but the principal idea of when to use the integration by substitution is what I just told you here, that again the derivative of what you substitute will be part of the initial, in the product of the initial function. So now let's continue. The third case, it's partial fractions. So So, of course, whenever you have a function which can be reduced in a rational function where the numerator, the degree of the numerator is less than the degree of the denominator, then of course you have to approach this problem using partial fractions. And of course, in this category is also the integration by completing the square, which it's a special case of this category here. So whenever you see a function which is a rational function, and you can, if the degree of the numerator is not less than the degree of the denominator, you just do the long division. You use the method of partial fractions. Now, the fourth choice that you have, it will be to use integration by parts. So, just let's remember what is the integration by parts rule. We have that the integral of the derivative of a function f times g with respect to x is equal with f g minus f g prime dx. So that's the integration by parts rule, which of course, okay, so that's the integration by parts rule. Some people, they prefer to use v and u. Me, I stick with f and g. It's the same thing, doesn't make any difference. So now if you look at the formula, of course, to calculate this here is not a problem, okay, as far as you can find the integral of f prime. The main thing is if you will be able to calculate this integral here. So, so we use this when we can, this integral here, it's easier than the original integral. There are some cases where it's obvious that you have to use integration by substitution, is when the f prime is equal with e to the x, or with cos x, or with sine x, and the g of x is equal with x to the n. So why? Because like if you have that f prime of x is e to the x, the integral of e to the x is e to the x, so you already know this here, and then you substitute the f also will be e to the x. So if you have, let's say that g is equal with x, so the derivative of x will be 1, so immediately you can find this integral here. Or let's say if it's x squared, doesn't matter, it will be 2x, and then you continue exactly the same process. You do one more time this integral, but still it's easy because the next time the 2x, the derivative of 2x, it will become 2. So, and again, it will have the e to the x in front, so it will be easy to find. And of course, when the f prime of x is one of these two, then we have what we call the loop case, because you have to do it twice in order to solve the problem. And finally, the last choice that we have is to use improper integration. So, I mean, here we have one case which is very obvious, like let's say if you have to find the integral of f of x dx, you know, let's say from a point A to infinity. I mean, you know immediately that you have to use improper integral because you have this infinity sign here, and of course you can have the infinity here or here, and of course it can be also negative infinity. So that's the improper integral type 1. Now, the one which is more difficult to see is when you have to find is the improper integral type 2. So where you have to find the integral of a function f of x dx from a point A to a point B, where in one of these points, the function f of x is not defined. So, for example, let's say you have to find the integral of 2 over x minus 1 from 1 to 3. Something that I forgot to tell you is that in improper integrals, we always deal with definite integrals. So let's say you have to find this integral here. So you see that this function is not defined at the lower limit. So in this case, you have to use, so this is an improper integral type 2, and we have to use the technique that we use for improper integrals. And I might upload a video for improper integrals in the near future. But for now, I'm just stressing the how you choose a technique to find an integral. So, I mean, you know, of course, the function can not be defined in the upper limit, and one which is also can be tricky. And again, you have to use the technique of improper integral, and again, it's type 2. It's when, let's say, you have to find the integral again, let's say, of a function known g of x dx from A to B, and the function is not defined in one point between A and B. Let me give you an example. Let's say you have to find the integral of, let's say, 3x over x minus 2 dx, and let's say you have to find this integral from 0 to 3. So you see that the x equal with 2, where this function here is not defined, okay, because it makes the denominator 0. So this value 2 is between 0 and 3. So that means that we have to break this integral into in two parts. It's the one from 0 to 2 and from 2 to 3. And again, because in 2 the integral is not the function is not defined, we'll have to use improper integral. So that was mainly the indications you had about what integral technique you will have to use in order to find a particular integral. So thank you for taking the time to view this video, and I hope you find it useful, and bye for now.